So we have seen two intuitive sorting algorithms, selection sort and insertion sort. Okay, but unfortunately for us, both of them turn out to be order n square. And we know that order n square is not really good enough for sorting large arrays. So what can we do instead? So here is one way to sort an array more effectively. So suppose we divide the array into two equal parts. So we just break it in the middle. We look at the left separately and the right separately. Now assume that we can sort the left and right into independently sorted halves. So we have the left half sorted and the right half sorted. Now if there were a way to combine the two halves efficiently to get a fully sorted array, then we can say that we have achieved the sorting by breaking it up into two smaller subproblems and combining the result. So let's first look at this combining step. Right? So we are given two sorted lists A and B, or two sorted arrays A and B, and we want to combine them into a single sorted list. So this is something that we can easily do. Supposing we had two stacks of cards in front of us, each of them is arranged in the same way in, say, an ascending order. Then what we would do is we would look at the topmost card in each stack and take the smaller of the two and move it to a new stack. And we would keep doing this until eventually we have moved all the elements into a new sorted stack. So this is an intuitively merging. So I have two stacks. So I have two stacks of cards. Right? So I look at the topmost card in each, and then one of them goes to a new stack, and then this is gone. And so now I look at the next value and compare it with this, and then one of these goes here, and so on. So eventually I build up a new stack of sorted things. So let's look at this in a very simple example. So supposing we want to merge these two sorted lists. So this is sorted in ascending order, and so is this sorted in ascending order. Right? So the first step is to look at the topmost. So let's assuming that in terms of topmost that these are written like this. So I have this stack and I have this stack. Right? So I look at the topmost element and then I say that the smaller of the two must be the topmost element of my new stack. Right? So in this case I take 21 out and I move it here. Now I have to compare what is the topmost element in the two stacks, namely 32 and 55. So now I compare the smaller of the two as 32 and move it out. Now I compare 55 and 74, and so 55 moves out. Now I compare 74 and 64, so now 64 moves out. Now I have nothing left in the second stack, so the first stack is in sorted order, so I just copy it out in order. So I first move 74 and then I move 89. Right? So this is a very intuitive merging thing that we do again quite naturally when we are dealing with physically two sorted lists, right? And we can do it with a normal array as well. So now how do we use this to sort? As we said, our aim is to break up the problem into two equal subproblems, solve the subproblems, and then merge the two solutions into a final solution. So we will sort A0 to A n by 2, A by n by 2 minus 1 to make it distinct. So we have A with indices 0 to n minus 1, right? So we take n by 2 minus 1 and n by 2 as the midpoint. So we sort this separately, and then we merge them. Right? So this is the strategy that we have, and this is, since the final step involves merging two solutions, this is quite naturally called merge sort. Now I've said that we will break up the thing into two subproblems. So how do I solve this? Well, I will recursively do the same thing. I'll break this up into two subproblems and I will merge this. I'll break this up into two subproblems and merge this. Right? So you keep breaking up the thing into subproblems until you reach a trivial subproblem, which is, as we have seen, which is an array of size 1. Okay? So let's look at an example before we proceed. So here is an example of an array that we would like to sort. So the first step is to break it up into two parts. Right? So we take the left part, so this is our midpoint. Right? So we take the left part, which is the first 4 elements, and the right part. And now we will apply merge sort separately to these parts. Finally, we will merge the answer. So having applied merge sort to the left part, you must again break it up into two parts. So I have to take this point and divide it into two parts. Right? And similarly on the right, I will have to take this point, okay, and divide it into two parts. Now, we could say that we can easily do arrays of size 2, but let's just keep going till we reach the base case. Right? The base case is when we have only one element and no sorting is required. So we'll again split each of these into two parts. Okay? So notice that for convenience we have taken something where I can keep dividing by 2, but there is no limitation in merge sort. It will work for any size. At some point when you do an unequal split, the two halves will not be the same size, but that doesn't really matter. Okay. So now we break the last step into two parts. So 43 is now, so this is in green to indicate that this is now a single element and hence sorted. So is this. And in the same way, we can take each of these last steps and get now 8 single elements which are sorted. Now we start merging, right? So we want to merge these two in order to sort that. And similarly, we want to merge these two. And we want to merge these two. And we want to merge these two. Right? So we merge the first two, and then when we merge this, the smaller one goes first. So this is now sorted. Similarly, we merge the second pair. It doesn't change in order because 22 is smaller than 78. We merge the third pair and they get exchanged. And we merge the fourth pair and again they get exchanged. So it is important to note this exchange did not come by looking at this array of size 2 directly, but rather by looking at these two values, taking the smaller one up first and then the bigger one. Okay. Now I want to merge these two arrays into a sorted segment of length 4 and these two arrays into a sorted segment of length 4. So again I apply merging. So note that 22 will come first, okay, then 32 will come here, then 43 will come here, and then 78 will come there. Right? So if I apply this, I'll get 22, 32, 43, 78. The same way here, 13 should come here, then 57, then 63, and then 91. Right? So this is the effect of merging. And finally, I have to merge these two. So the smallest one, 13, will go here. Then I will get 22. Then I'll get 32. Then I'll get 43. Then I will get 57. Then I will get 63. I'll get 78. And then I'll get 91. Right? So merging these two sub-arrays of size 4 will give me the final answer. Right? So this is how merge sort works. You break it up into two parts, recursively solve the two parts using the same strategy, and merge them. So this is generally a principle that can be applied to many problems. So if you can take a problem and divide it into two or more parts, okay, such that this part can be solved independent of that part and there is no overlap. So you solve this separately, you solve this separately, and now you want to somehow combine. In this particular algorithm, the combination is merging. We will look later on at other divide and conquer algorithms where the combination might require a different strategy. But the whole idea is that if you can break up the problem into smaller problems and then combine them, then you can sometimes get a lot of benefit in terms of efficiency. Okay? So the crucial thing is to identify how to break up the problem into disjoint subproblems and how to combine the solutions to these subproblems efficiently to solve the problem at hand. So let's come back to our merge sort and try to formalize the algorithm in terms of actual code. So how do I combine two sorted lists or two sorted arrays A and B into a third sorted list C? Well, as we saw, if one of the two is empty, then I don't have to do anything. I just have to copy the other one. So if there is no element left in A, then I can just copy the rest of B into C. If B is empty, I can copy A into C. Otherwise, we compare the first element of A and B and move the smaller of the two into C, and we repeat this until everything has been moved. Right? So here is a simple iterative merge function. So it takes two arrays as input. It takes an array A of size m, so 0 to m minus 1. And it takes an array B, which may be of a different size, 0 to n minus 1. And the aim is to construct a new array C. Now we know the size of C because everything there must come here. So it will be 0 to m plus n minus 1. Right? So what we do is we maintain some position. So we say that, okay, let I be the current position I'm looking at in this, J be the current position I'm looking at in B, and K be the current position I'm trying to fill in C. Right? So now we know that there are m plus n steps. So we put a loop which says that this thing must run m plus n times. Okay? So if we have already reached the end, if J has already reached the end, okay, or if AI is smaller than Bj, right? So this is the real merge step. If AI is smaller than or equal to Bj, what we will do is we will copy this value here, and then we will increment I and we'll increment J, right? So we will move Ck will be AI and I will be incremented and K will be incremented, okay? So but this also happens in case J is equal to n. Because if J is equal to n, what it means is that this pointer has actually reached all the way there, so there's nothing left to scan. So J is equal to n means it's actually beyond the right point, right? So it's beyond that. So there's nothing to scan, and so we will just copy everything from A to C. So either we copy the current element from A to C if AI is smaller than Bj, or if there's nothing in B, we copy the current element because we are just copying everything from A to C. So the symmetric case is when we have AI bigger than Bj. So if AI is bigger than Bj, right, then what we want to do is copy this value here. So we want to move J up and K up. So we copy Ck is equal to Bj, copy the value at Bj to Ck, and increment both J and K. And like we did earlier, the other reason we might want to do this is if we have already exceeded the length of, so if we are currently here, so A has been exhausted, then we would also move the next element blindly from B to C. Okay, so this is a simple while loop, right? It takes exactly as many steps as there are elements to move, and in each step I move one more element to C, either from A or B, depending on the criterion of the current element I'm looking at. So having got merge out of the way, now we can look at merge sort itself. Right? So if we want to sort A of size n, indices 0 to n minus 1, we have to create a new array, as we said, because merging has to copy the two things into a new thing. Right? So we're eventually going to take A and merge sort it into a new array B of the same size. So if n is 1, if we have an element of size 1, we have the base case and nothing is to be done. Right? Otherwise, we will sort the left part into a subarray L, we'll sort the right half into a subarray R for left and right, and then we will merge the two using the function we just wrote. So this is a very clear recursive algorithm. So we want to merge sort A from left to right. So we will assume that when we say from left to right, we mean that the leftmost position is called left, right, and the rightmost index is actually right minus 1. Right? So this is actually one more than the index of the position that we want to sort up to. So we want to sort the segment starting at A left and going up to and including A right minus 1. So first of all, if this segment is of length 1, right, then we just copy the value into B. We copy the value at A left, right? Otherwise, what we do is we find the midpoint, right? And then we copy up to but not including mid. This is why we use this convention that it's up to mid minus 1. So this will be from left, A left to A mid minus 1. And this will merge sort from A mid to A right minus 1, right? So what we want to make sure is that we are not accidentally overlapping. So we want to make sure that this mid value which appears in both things, the value at A mid is only in one of them, namely it's in the right hand side, not in the left hand side. So having done this, then I will use my earlier merge function to merge L, which is of size mid minus left, and R, which is of size right minus mid, into B. Right? So this is the function that we already had before. So it's a very simple recursive thing. Find the midpoint, sort the left half, sort the right half, and merge them. Okay? As we said, it doesn't really matter that A is of even length or it's a multiple of 2. So it might be that the left half and the right half are not of same length. One will be longer, one will be shorter. It doesn't really matter. This works in all cases. To analyze this is not so straightforward, so we will postpone that to the next module.